So hello to everyone who's watching on YouTube. So since no one has joined the session yet, so I'll be waiting for people to join the sessions. So I'll start discussing the problems in like 5 minutes. So yeah, I'll start in 5-6 minutes so that maybe some students can join the session. So yeah. Okay, so since no one has joined the live session yet, so I guess I'll just start discussing the problems then for the YouTube audience who's watching. So yeah, I guess I'll start. So first of all, let me just reintroduce myself. So I'm Lakshay Saggi, the discrete math problem solving TA for the Tuesday sessions, and this is our 12th and last problem solving session for at least this semester's discrete maths course. So in this session, I'll be discussing problems related to like the contents of this week, which were based on rings and fields and stuff. So yeah, a bit of abstract algebra. So yeah, and note that even though this is the last problem solving session, uh, I'll also be holding a summary session, a 2 hour summary session tomorrow. I believe the announcement about that will be on the NPTEL webpage only. I, b- as far as I think, the tomorrow session is scheduled from like 10 p.m. to like 12 in the night. So yeah, it will be a 2 hour summary session basically where I'll be discussing uh, topics which we covered through whole 12 weeks. So yeah. So hope to see you guys in the tomorrow session also. But yeah, let's just focus on the today's session first of all, like the session in which we discuss problems related to rings and field and stuff. So yeah, so maybe I'll just start sharing my screen and I can start discussing the problems. So yeah. Okay, so I have started sharing my screen now. So, like I usually do in all the sessions. So, first of all, I like to start off with a bunch of preliminaries, the basic definitions and stuff which was covered in this week, just to get everyone on the same page. And then I'll start discussing the problems. So yeah, just a bit of definitions and preliminaries first of all. So as I already told you guys, this session will be more about rings and fields and stuff. So what is a ring? So last week we had covered what are groups, and now in this week we'll be discussing what are rings and what are fields. So what's a ring and what's a field? So let's just see what the ring is. So I'll just taken the definition directly from the lectures. Like you can also view these definitions in the lecture videos, but just to save you the hassle, I just took a screenshot of the definition from the lectures. So yeah. So note that these preliminaries are not a substitute for watching the lecture videos because they cover everything in much more detail. But yeah, I just like to give a bunch of preliminaries so that everyone can, if you have some forgot some part of some definition or something, maybe you can instead of watching the whole lecture, you can just get it done using these sessions. So yeah. So what's a ring? Basically, a ring is a set R with binary operations defined which are plus. We call this the addition of the ring and the multiplication of the ring over the set R, and it's called a ring if all the following conditions hold. So note that earlier in last week we had covered what are groups, and in groups what we had said was there is a set G and there's a one operation associated with that set. And now while defining a ring, we are actually associating a set with two operations, which are like one is sort of addition. This is not the integer addition, but some operation which we'll define, and it should follow some properties, and similarly a multiplication operation. So the properties which should hold for being a ring are first of all the set R comma addition, the addition of this ring should form an abelian group. So remember what's a group. So this R comma plus should first of all form a group, and a group which has commutative properties is called an abelian group. So this R comma addition should first of all form a group. And what's the definition for being a group? the properties which should be satisfied for forming a group are it should have a closure property that like if A and B belong to that group, then A plus B should also belong to that group. This is the closure property. Then there was the associativity property, which is like for three elements of the group A, B, and C, A plus B when added with C should be equal to A added to B plus C, something like this. So note that this is not the like again, I'll just like because we are doing abstract algebra, I'll just remind you guys again and again that this is not the actual addition over integer or something. This is just a operation which we have defined, and this operation is an abstract operation which could be doing anything which we don't know. And like it will this operation will be defined for will be different for different groups and stuff. So yeah. The third property for being a group is existence of an identity element. So there should exist an element 0, which is denoted by 0, such that a plus 0 should be equal to 0 plus a, which should be equal to a itself. So it's called the identity of the group. And similarly, the last property is that for every element, there should exist an inverse. So for every element a, there should exist an element minus a, such that a times minus a plus minus a should give me back the 0, which was the identity element. So yeah, and note that these were the properties for a group. And now we want that R comma addition should be an abelian group. So abelian group is a group in which commutative property also holds. So commutative property is nothing but for all pair of elements A comma B belong to the group, A plus B should be equal to B plus A. So these are the first set of constraints. Like these are the first set of properties which should be satisfied for being a ring. Note that the other set of properties which should also be satisfied, like this set of R1 should be satisfied, R2 should be satisfied, and R3. All these three should be satisfied for it being called a ring. So the second set of properties which should be satisfied are by this dot operation, or I personally like to call it the multiplication operation over the ring. So the multiplication operation should satisfy closure, associativity, and identity properties. So note that for the addition operation, we have defined the properties closure, associativity, existence of inverse, and existence of identity, and commutativity. But here we just take three of those properties for the multiplication part. So addition should satisfy these five properties, but multiplication should only satisfy these three properties, which are closure. So for any two elements A, comma B belong to the R, the element A times B should also belong to R. Similarly, associativity, A times B when multiplied by C should be equal to A multiplied by B times C. And the third property is the identity property, that there should exist an element 1 such that for all elements A times 1 should be equal to 1 times A, which should be equal to A. So note that the identity which we had discussed earlier, this was there should exist an element 0 such that A plus 0 should be 0 plus A, which should be equal to A. This was the identity element with respect to this addition operation, or one of the operations of the group. And this identity 1 is over the multiplication operation. So note that these identities may differ. Like uh, these elements may differ. So these are two different identities. This is called the multiplicative identity of the ring, and this is called the additive identity of the ring. So keep that in mind, guys. Like these two elements, 0 and 1, are actually not equal elements. And note that these are not actually integers, also the 0 and 1 integers. These are just notations for the multiplicative identity and the additive identity of the ring. So yeah. So the multiplication operation should have closure, associativity, and identity. And now, so sort of like this operation, this multiplication operation over set of matrices also works, right? Um, if R was set of matrices, then and this dot was standard matrix multiplication, then we know that a matrix times a matrix returns a matrix. Similarly, a matrix A times a matrix BC is equal to matrix AB times a matrix C. And there's an identity among the matrices, which is the uh, identity matrix, which has all diagonal elements as one and every other element as zero. So like at least in matrix, if this R group was, if this R set was set of matrices and this was matrix multiplication, then at least these are R2 set of properties are satisfied in that case. So just like giving you an example where these set of properties are satisfied. And the R3 set of properties should also be satisfied, which is the distributive property. So why have we divided these set of properties into these three sets of properties R1, R2, and R3? So that this R1 set of properties deals only with the additive operator. These properties should be satisfied by the addition operator. The R2 set of properties should be satisfied by the multiplication operation. And now since both of these operations are defined over the set R, we need a set of properties which relate this addition and multiplication also. Otherwise, like we could have just defined uh, two separate entities, which was R comma plus and R comma multiplication. So we relate this addition and multiplication by this set of properties, which are the distributive properties, or well, let's say the distributive laws. So what it says is that for any three elements A, B, C belong to the set R, the element A times B plus C should be equal to A times B plus A times C. So we should be able to take like what we call expand, or let's say take out the stuff from parentheses and write it like this. Similarly, A plus B times C should be equal to A times C plus B times C. So yeah. So this is something which is called the distributive laws, and like so this R1 set of properties along with R2 set of property and this R3, which is the distributive laws, when all of these three together hold, then we call that entity a ring, basically. So this is a definition of a ring. So yeah, in abstract mathematics, sometimes the definitions can get a bit confusing, but if you just view it as a whole, like so we just need the addition to satisfy some properties, multiplication to satisfy some, and then these two properties interact by distributive laws. So this is the definition of a field. This is the definition of a ring. And now what is a field? So a field is somewhat of a more restriction over a ring, or let's say a ring is a generalization of a field. So in field, in field, all the properties of this ring should be satisfied along with some more properties. So let me just give you guys an example, or let's say I'll just give you guys a definition of a field. So this is again from the lectures itself. So the f, basically a set f comma this addition operation comma this multiplication operation as you defined over a ring is a field if all of the following hold. So f comma plus should be an abelian group. So similarly in rings also this addition should have been an abelian group. Then the second set of properties. So first set of properties was an abelian group. And then the second set of properties, these F2 properties differ from this set of R2 properties. So in R2, we only had closure, associativity, and identity. But what these F2 properties says is that the set F minus 0, where 0 is actually referring to the additive identity of the field. So this set F minus 0, comma this multiplication operator should form an abelian group. So addition should form an abelian group. Similarly, multiplication should form an abelian group also. So note that what properties are essential for being called an abelian group. The properties are basically closure, associativity, existence of identity, existence of inverse, and commutativity. So why in the definition of ring, we only had closure, associativity, and identity. So only the additional two properties which are defined over the field are the commutative property and the existence of inverse for every element. So only these two extra properties are defined. So these are the two properties which differ between R2 and F2. That R2 does not have commutativity and existence of inverse, but F2 has. So this is the only difference. And then this set of F3 and R3 properties are the same, the distributive laws. So A times B plus C should be equal to A times B plus A times C, and A plus B times C should be equal to A times C plus B times C. So essentially what you can think is that a field is nothing but a ring uh, which has whose multiplication operation also has inverse and commutative property. So yeah, so fields are somewhat nicer because they have some more properties than rings. So yeah, so so just to view it like this, so what we can essentially state is that a field is nothing but a ring. So note that all of this is from the lectures itself, but I am just putting it here so that it's easier for everyone to follow. So what we can essentially state is that a field is a ring where every non-zero element is invertible. So this is, maybe I shouldn't delete this part, but yeah. So this is what everyone should keep in mind, that this is what a field is. Uh, Field is a ring. Okay, so yeah, a field is a ring where every non-zero element, basically instead of F2 properties, we are not using the zero. So every non-zero element of the set should be invertible. And also this multiplication should have uh, the commutativity. I think the commutativity has not been described here, but yeah. So maybe I should just delete this part. Let's just keep it as simple as this, that this is the definition for field and this was ring. The only differences which we see are in R2 and F2 properties. So in F2, basically, we also need multiplication to have inverse properties and also commutativity. So fields are, as we see, somewhat nicer. So note that there are also a bunch of definitions more defined in the lectures. What is the order of a field? What's a characteristic and stuff like that. But I'll not be getting into that. Maybe you guys should watch the lectures for uh, like getting to know what all definitions exist. But I just wanted everyone to be on the same page, at least regarding the definitions of a ring and a field. And now maybe we can start with discussing the problems then. So yeah. So I have a set now of like 5 problems defined, and I believe it shouldn't take a lot of time to cover these problems, but yeah, I'll just get started then. So yeah. So the first problem states that consider the polynomials px, qx, rx, and sx over a field f. So what's a polynomial? What do you mean by a polynomial defined over a field f? Again, this is something which has been covered in the lectures, and I believe if you don't know about this, you should watch the lectures because yeah, there are a bunch of definitions when you're just starting out with abstract algebra. There are a bunch of definitions which you need to see to at least understand how are we defining stuff and all. So once definitions become clear, then everything sort of follows easily. So the main part of getting to understand or getting started with abstract algebra is getting to know with all these definitions, like what's a ring, what's a group, what's a field, and then getting a feel of everything. When you get a feel of everything, then the problems are uh, at least at the beginner level, quite easy in nature. So yeah. So basically, if we consider the polynomials px, qx, rx, and sx over a field f, which satisfies the equations px equals to qx times rx and qx equal to px times sx, then we need to choose the correct statements from the following. So we know we are given that px is equal to qx times rx and qx is equal to px times sx. So note that all of these are polynomials over a field, and we want to see which of these statements are correct. So options are like the polynomial px is a constant, qx is a constant, rx is a constant, or sx is a constant. So yeah. So one thing to note here is the hint here. Like this hint is like something not out of this world. It's a simple hint that this has also already been discussed in the lectures also, that polynomials over a field cannot have negative degree. So, yeah. So just note that polynomials over a field cannot have negative degree, and a property of polynomial multiplication over a field over the set of fields is something which maybe I should define here. So property. Uh, And this property is something which I'm not defining on my own. This has already been discussed in the lectures, but I'll be using this property to solve this problem. So the property is that if Px, Qx, and Rx are polynomials over a field F such that uh, Px is equals to Qx times Rx. So if Px is actually equal to Qx multiplied by Rx, then what we can say actually, we can have a very nice property that then degree of Px is actually equal to uh, degree of Qx. So essentially, if we are doing polynomial multiplication over fields, then the degrees of Qx and Rx add up. So actually, degree of this polynomial Px will be nothing but the sum of degrees of Qx and Rx. So degree of Qx plus degree of Rx. So you might think that why am I writing this property like this is like, so this property is somewhat trivial for at least the polynomials which we know, which are defined over rational numbers, that degree of a polynomial is equal to sum of degrees of the two polynomials which are being multiplied. So you might think that this is a very simple statement, but note that these polynomials are defined over a field and uh, not over the real numbers or something. So for a field also this sort of property is satisfied, and it's not like obvious like you need to prove it and stuff, and you can see the proof in the lectures itself. And like if these polynomials were instead defined over a ring instead of a field, then this property does not hold. So yeah, so you should keep in mind that this property should not be taken for granted that, oh, this is obviously true, but yeah, there's some nuance to it. So yeah. So then maybe uh, if we know this, and we also know that polynomials over a field cannot have a negative degree, so we know two things. Like here we are given that Px equals to Qx times Rx and Qx equal to Px times Sx. So first of all, we know that Px equals to Qx times Rx. So what we are given is Px is equals to Qx times Rx, and we are also given that Qx is equals to Px times Sx. All of these are polynomials over a field. So what does this imply? This implies that. So the first thing implies, like from this property that we have, the first statement implies that degree of Px is actually equal to degree of Qx plus degree of Rx. Right? And similarly, what does this statement imply? This statement implies that degree of Qx is equal to degree of Px plus degree of Sx. So degree of Qx is actually equal to degree of Px plus, or maybe I should just keep it one at a time. So what we are given is Px equals to Qx times Rx and Qx equals to Px times Sx. So from this first statement, we know that degree of Px is degree of Qx plus degree of Rx. And what does this imply? This implies that also we know that polynomials over a field cannot have a negative degree, right? So this term is non-zero. This term is like this term is non-negative. This term is non-negative. This term is non-negative. So all are greater than or equal to 0. So essentially we can say that degree of Px is equal to degree of Qx plus some non-negative quantity. So at least we can say that degree of Px is actually greater than equal to degree of Qx. Right? If we want to eliminate this Rx, then we can say something like degree of Px is actually greater than equal to degree of Qx. So let's just say this is statement 1. So yeah. So statement 1 says that degree of Px is greater than equal to degree of Qx. And also something else we know is that Qx is equals to Px times Sx. This is also given to us. So this means that degree of Qx will actually be equal to, maybe I should just copy this, that degree of Qx will actually be equal to degree of Px plus degree of Sx. So degree of Px plus degree of Sx. And what does this mean? This implies that, again, since degree of Sx is greater than equal to 0, so we can say that degree of Qx will be greater than equal to degree of Px. Let me just write it down. So we can essentially say that degree of Qx is greater than equal to degree of Px. So yeah. So I guess everyone would have already seen what I'm trying to show here. So first from 1, we prove that degree of Px is greater than equal to degree of Qx. And here we have proved that degree of Qx is greater than equal to degree of Px. So this essentially means that if A is greater than equal to B and B is greater than equal to A, this means that A is actually equal to B, right? So from 1 and 2, we get that. What do we get? We get that degree of Px is actually equal to degree of Qx. So from 1 and 2, like degree of Px is greater than equal to degree of Qx, and degree of Qx is greater than equal to degree of Px, we get this thing that actually both the degrees are equal. So if both the degrees are equal, then maybe we can. So if these degrees are equal, then what we can actually do is maybe just put it into the original equation. So we know that initially we knew that degree of Px was actually equal to degree of Qx plus degree of Rx. So what does this imply? This implies that degree of Rx is actually equal to 0, right? Why is that? Because we know degree of Px is degree of Qx, and if we put that here, here we had degree of Px is degree of Qx plus degree of Rx. So if these two terms are equal, then they get cancelled out and we get degree of Rx is actually equal to 0. And similarly, if we put degree of Qx is degree of Px here, then again these two terms will cancel out and we'll get degree of Sx is actually equal to 0. So degree of Rx is 0 and degree of Sx is 0. So we get something like this, that degree of Rx is 0 and degree of Sx is 0. And note that degree 0 polynomial is nothing but a constant. So what we essentially get is that Rx is a constant and Sx is a constant. And also degree of Px is equal to degree of Qx. So the options are asking which of the polynomials are constant. We get that degree of Rx and Sx is 0. So these are the constant polynomials. So Rx is a constant and Sx is a constant. So Rx and Sx are constant polynomials. So yeah. So what's the correct answer? Hence options C and D. C option was Rx is a constant and D was Sx is a constant. So option C and D. Correct. Okay, so yeah, I guess this was a pretty straightforward question, like just the application of this thing and this thing. Maybe I should write the reasoning here also. Why is this true? Okay, so someone has joined the meeting. So yeah, so uh, hello Dishu. I believe you have just joined the meeting. So I was just till now I've just discussed the basic definition of what's a ring. I just want to remind everyone what a ring is, and then what's the definition of a field. And then I was just discussing this first question, and yeah. So the question is like quite straightforward. If we all and I discussed it just now, maybe you can have a look at the question and the solution which I have given, and if you have some doubt in that, you can ask me via chat. So yeah. So the first question was nothing but we were given polynomials over a field, px, qx, rx, and sx, such that px is qx times rx and qx is px times sx. And we need to identify which of the polynomials are a constant polynomials. So we know that since px equals to qx times rx, we can write that degree of px is equal to degree of qx plus degree of rx. And since polynomials over field cannot have negative degree, this implies the degree of px is greater than equal to degree of qx. So similarly, we again have degree of qx is greater than equal to degree of px here. And from that, we get degree of px is actually equal to degree of qx. And from that, if we put this into this equation, we essentially get that degree of Rx is 0. And similarly, we get that degree of Sx is 0. And the degree 0 polynomials are nothing but constant polynomials. So yeah. So I hope this is a straightforward question and you were able to get it. If you have any doubts, you can ask me anytime via chat and I'll try to explain to best of my capabilities again. So yeah. So for now, I'll move on to the second question then, since I just finished discussing this first question. So yeah. So coming to the second question. So second question is nothing but match the following question. So the question asks, uh, the question is asking like, so we are given these A, B, and C, and we need to match it to 1, 2, and 3. So the first question is characteristic of Z3. So note that, so we'll be doing it row by row. So I guess we can start with row A. So we want to find out what is the characteristic uh, of this field Z3. So note that we are just given Z3, but what it essentially means is that for something to be a field, we need to define the addition and multiplication operations also. So whenever we are just given the set of Z3, you can just assume like if we are given the set Zn, that the multiplication and addition operations are just regular integer multiplication and addition modulo n. So the field here in the question is like the set of numbers 0, 1, and 2, and modulo 3 addition and modulo 3 multiplication. So that's the field which we are talking about in this option A. And now we want to find out the characteristic of this field. So first of all, what's the characteristic of a field? This has been discussed in the lectures also, but maybe I'll just define it again. So characteristic of a field. So characteristic of a field is nothing but the number of times the multiplicative identity. So I guess I should keep it like this. Yeah. I should underline this. So yeah, so just underlining like that I'm writing the definition of a characteristic. Number of times the multiplicative identity of a field should be. So we know that in a field, multiplicative identity always exists. Similarly, we also note that additive identity of a field also exists, right? Because in a field which we had already defined that addition and multiplication should form groups, abelian groups, and in groups, always a multiplicative and additive identity exists. So yeah. Okay. Why is okay? So someone else has also joined. So Priyadarshini has joined the session. So hello, Priyadarshini. I'm just discussing the second question now. Like I had just finished discussing the first question, and now I've just started with this second question of match the following. So yeah. So first, I was just defining what a characteristic of a field is. So characteristic of a field is nothing but number of times the multiplicative identity of a field should be added. So note that this added is not the integer addition, but rather the fields addition operation to obtain the additive identity of the field. So the minimum number of times the multiplicative identity of a field should be added to obtain the additive identity of a field. So we know that there is some multiplicative identity of a field because like fields over multiplication form like the set for over a field is defined such that the inherent set of the field should over the multiplication should form a group, an abelian group, and similarly over addition of it should form an abelian group. And we know that in groups, there exists additive and multiplicative. Like there exists identities in groups. Like this is the definition of both. So that's why we know that this multiplicative identity and additive identity exists. And now the characteristic of a field is the minimum number of times the multiplicative identity should be added to obtain the additive identity. So how many times should we add the multiplicative identity together to obtain the additive identity of the field? And that's what is called the characteristic of a field. So, so we know that for field Z3, uh, we know that additive identity. So as I defined earlier, also the addition operation when whenever we write this Z3 or let's say any Zn, the addition operation is generally defined as the set the operation of integer addition modulo n, and similarly multiplication is defined as the integer multiplication modulo n. So for field Z3, additive identity is nothing but 0, and multiplicative identity is nothing but a 1. So for field Z3, the additive identity is 0 and multiplicative identity is 1. And now to find out characteristic of a field, we know the definition of characteristic. The minimum number of times the multiplicative identity should be added to obtain the additive identity. So how many times should we add this 1 to obtain this 0? And note that this addition is over this field of Z3. So we know that it's easy to see that since 1 plus 1 plus 1, so if we add this 1 3 times, we actually obtain 3, which modulo 3 is actually equal to 0. Since we are in field Z3, we'll be dealing with like modulo 3. So 1 plus 1 plus 1 is actually equal to 0 in field Z3. So what does this mean? We needed to add 1 3 times to obtain a 0. So the characteristic of this field Z3 is actually equal to 3. since the number of times we needed to add the multiplicative identity, which was 1, to obtain the additive identity, which was 0, was 3. So this implies that characteristic of Z3 is nothing but 3. So yeah, maybe I should underline this, or maybe I guess we can put it. So yeah, so this row A should be matched to this option 3 here. And now let's come to the second question then. The second row, which is number of fields in the set Z4, Z3, and Z2. So note that I already assumed that Z3 is a field because I already knew that Z3 is a field. And that's how we define characteristic and stuff. But here we, in the second question, like we actually need to identify which of these is a field. So note that again, addition and multiplication are defined modulo n over Zn. So like for Z4, we'll define addition over modulo 4. Similarly, over Z3 over modulo 3 and Z2 over modulo 2. And we need to see which of these is actually a field among Z4, Z3, and Z2. Uh, which of these sets actually form a field. So note that one thing to keep in mind, this has been discussed in the lectures also. So uh, property which we should keep in mind is that Zn forms a field if and only if n is prime. So if this n here is a prime number, then we can say something like, and I'm defining this for n greater than equal to 2, obviously, because for n equal to 1, this will be nothing but the set 0, and this will always be a field. So that's like a very trivial field, but in terms of non-trivial fields, I'll be saying that Zn forms a field if and only if n is prime. So if this n here is prime, then we will say that it is a field. So like here 3 was a prime, and that's why I'd like intuitively said that this is a field and we can find out its characteristic. So among these options, Z4, Z3, and Z2, only 3 and 2 are prime, and 4 is not a prime number. So that's why Z4 will probably not be a field. Okay, I think this statement is also not correct. Okay. Uh, okay, maybe I think you should take this statement with a pinch of salt because I believe pseudo primes can also satisfy this. Okay, let's just keep the statement as it is for now, and maybe if there is some change to it, I'll edit it in the docs which I upload. So yeah, and I'll talk about it in the summary session which we have tomorrow also. So yeah, so for now, let's just assume that the statement is true, but I'm not sure. I just realized maybe this statement might have some counterexample, but yeah. For now, let's just think that Zn forms a field if and only if n is prime. And so it's easy to see that here Z among Z4, Z3, and Z2, only 3 and 2 are prime. Since 2 and 3 are prime numbers, hence Z3 and Z2 are fields. So, okay, maybe we should, instead of writing this as if and only if, one property which I'm sure that this always works is that Zn forms a field if n is prime. So if this n is a prime number, then always we'll have a field. So since 3 and 2, but if n is not a prime number, then um, I'm not sure, like maybe we can get a field or maybe we don't get a field. Let me just think about it for a minute. So yeah, I think we can keep it like this. Like, Zn is a field if and only if n is prime. And now since 2 and 3 are prime numbers, hence we know that Z3 and Z2 are fields and Z4 is not a field. So the number of fields among the set Z4, Z3, and Z2 is just these two fields. So Z3 is a field and Z2 is a field, but Z4 is not the field. So set Z3 and Z2 are fields. So there are two sets which are fields here. So the answer is 2 here. So the row B is matched to row 2 here. So yeah. So this implies that there are two fields. That is Z, C, and Z. So yeah. So note that guys, if you have any doubts, like I just stopped here. Like, I got a bit confused here, so maybe like so I try to clarify it. But if you guys still have some confusion, like what I was trying to say here, you can ask me via chat. I'll try to explain again. But the only thing which I want to say was like Zn forms a field if and only if n is prime. Yeah, nothing else. So that's how we say that since 2 and 3 are prime numbers, Z3 and Z2 are fields, and Z4 is not a field. So there are two fields here. And now coming to the row C. So the row C asks us the number of primitive elements in the multiplicative subgroup formed from the field Z3 plus and dot. So the primitive elements, so maybe like we can like for now we can just see that since row A is matched to 3 and row B is matched to 2, like this row C will get matched to 1 itself. So it's like but the solution like number of primitive elements in the multiplicative subgroup formed from the field. So if we are given this field of Z3 and this standard multiplication and addition operation, and we want to find out the number of elements in the multiplicative subgroup. So what will be the multiplicative subgroup which will be formed here? It will be basically what I'm trying to say here is this is a very straightforward question, and like the multiplicative subgroup will be nothing but the set 1 comma 2 itself, and like the 2 will be a generator for that set, and so 2 will be a primitive element. So uh, maybe I should write it down. So what will be the multiplicative subgroup? Multiplicative subgroup will be the subgroup formed over the multiplication operation over this set of numbers. So over the number 0, 1, and 2, the multiplicative subgroup will be just the set, thus the group formed by the numbers 1 comma 2. So so maybe like what I want to point out is like this is a very trivial problem, and like maybe you guys should see from the lectures what the primitive element and what does multiplicative subgroup mean. But I'll just write down the solution here. So what will the multiplicative subgroup here? It will be the set of elements 1 comma 2, and the primitive element here will be, so primitive element is nothing but the element from which the whole subgroup can be generated. So if we take this one and if we multiply this one k number of times, we'll still get a 1. So from this, we can't generate this group 1 comma 2. But if we take this 2 and if we multiply this, if we take 2 squared, then 2 square modulo 3, since we are dealing with Z3 field, will actually be equal to 1. And if we again multiply it with 2, we'll obtain 2 again. So the whole multiplicative subgroup can be generated using this number 2, but it can't be generated using this one. And that's why 2 is a primitive element, but 1 is not a primitive element. And note that what's a multiplicative subgroup? The multiplicative subgroup is just this. For a field F, the multiplicative subgroup is just the group formed by the elements of F, like barring the zero element, like which we did here also, like this F minus 0, comma dot. This is what we call a multiplicative subgroup for a field. This definition, F minus the additive identity, which is 0. So if we remove the 0 from the set and take the remaining elements and we define the operation as the multiplication operation, then that's what we call a multiplicative subgroup of the field. So here the multiplicative subgroup will be 1, comma 2 because we have removed 0 from this. And the primitive element for this subgroup will be nothing but the element which can generate. And a primitive element for this subgroup will be an element which can generate all the values of this subgroup by using repeated multiplications. And we know that 1 times 1 times 1, if we take any number of times, it will still give you a 1. But 2 squared, like 2 raised to the power 1 will give me 2. 2 raised to the power 2 will give me a 1 here because 2 square modulo 3 is actually equal to 1. And the primitive element here is 1. 2. And primitive element is 2 here. So yeah. So what does this imply? This implies that there is only one. So note that there can be more than one primitive elements also, but at least for this multiplicative subgroup of 1, comma 2, there is exactly, there is only one primitive element. So we have this solution, like I'll just put this in bold. So just put this in bold. So for row A, we have the solution as 3. For row B, we have this 2. And for C, we have this 1. So the correct answer is, hence the correct answer is, since we need to match, A is matched with 3, B is matched with 2, and C is matched with 1. So yeah. So yeah. So I hope this is clear to everyone. Like first of all, what's a characteristic of a field? Like it was an easy definition. Then when is the field Zn? When does the set Zn form a field? And then like what's a primitive element of a multiplicative subgroup? So if you have any doubts in any of these three, maybe you can let me know via chat. I'll try to answer your doubt. So if everything is clear to everyone, then maybe I can move on to the next question then. So since no one is typing anything in the chat, I'll just assume that it's clear to everyone. So yeah. So let's move on to the next question then. So so the third question says that asks us the values of C for which this x square, the polynomial x square plus C is irreducible over Z3. So yeah, again, a question for which you need to know what does this term irreducible, what does a polynomial being irreducible mean? So overall, just to give you guys an intuition of what does the being irreducible mean. Irreducible means that that this polynomial cannot be broken down into smaller factors with respect to this field Z3. So with respect to this field Z3, this polynomial x squared plus C should not be broken down into like smaller factors. If we are able to reduce it to smaller factors, then it's not irreducible. Like irreducible is something which cannot be broken down into smaller degree factors. And a reducible polynomial is which can be broken down into smaller degree factors. So, and the field over which we are defining the polynomials is just the field Z3. So yeah. So one criteria, so there's another property, or let's say theorem, or anything you can say, uh, that polynomial over a field is irreducible uh, if and only if there does not exist. Okay, maybe I should not write it like this. Um, mm, so, so how should I write this? I'm just thinking about it. So yeah. So one thing which we definitely know is, so a property is that a polynomial is reducible. So I'm writing that a polynomial is reducible if, note that it's not an if and only if condition, but rather just an if condition. That, or maybe I should write it like this. If there exists a zero of the polynomial in the field F, then the polynomial is reducible. If there exists a zero of the polynomial in the field F, then the polynomial is reducible over F. So if we are given a polynomial and there exists a zero of that polynomial in the field F. So what I mean to say is that they over the field F, like the field F, the set F contains some values. If one of the values satisfies that, if we put in that value in that polynomial, uh, the value comes out to be zero. Where again the multiplication and addition of the polynomials are defined over the field operations and not rather just integer or like real numbers addition and multiplication. So if there exists a zero of the polynomial in the field F, then the polynomial is actually reducible over F. And like this property is not too hard to prove, because if alpha is a zero of the polynomial, then x minus alpha is actually a factor of that polynomial over the field F. So this is something which has been discussed in the lecture, and it's not too difficult. So yeah. So this is a property. So just looking at this property, maybe we can go option by options. So, so note that this is not an if and only if condition. So this just states that if there exists a zero, then the polynomial is irreducible. But it does not state if what happens when there does not exist a zero. So actually, if there does not exist a zero, then also it may be possible that polynomial is reducible. So we'll need to check for that, like which specific polynomial is reducible or which is not reducible. But at least when there exists a zero, then it is reducible. When there does not exist a zero, we don't know whether it is reducible or irreducible. But at least if there exists, then we are sure that it will be reducible. So yeah. So maybe we can go option by option. So values of C for which this polynomial x square plus C is irreducible over Z3. So the option A is x square. So if we put here in option A, we put C equal to 0, then the polynomial is nothing but x square plus C is, if C is 0, then this polynomial is nothing but x square. Polynomial is nothing but x square. And note that we don't even need this property to say that this polynomial is reducible. So I'm claiming that this x square polynomial is reducible. and we don't even need this property. Just saying why is this polynomial reducible? It's reducible because this polynomial can be written down as x multiplied by x times x. So yeah. So this polynomial x square, like a polynomial defined over the field Z3 should have the coefficients as only 0, 1, and 2 because Z3 contains only the elements 0, 1, and 2. And polynomial defined over field F should only have coefficients belonging to that field. So x square has a coefficient 1, and now the two polynomials which are of lesser degree than the original polynomial should also have coefficients from the field Z3 only for the polynomial to be called reducible. So here we see that the first polynomial x and the second polynomial x, both of these polynomials have coefficients of 1, which are in this field Z3. So since x square can be written as x times x, um, so this is actually reducible. Hence, the polynomial is reducible here. Like we didn't even need to invoke this theorem. We can just directly say. And if you just want to invoke this theorem for the purpose, like just for sake, you can just see that putting x equal to 0 gives the value of this polynomial as 0 square mod 3, which is nothing but 0 itself. So that's why the polynomial is actually reducible. So yeah. So instead of coming to option B first, I'd like to come to option C first. So option C states that so option C is nothing but a polynomial is given as x square plus if C is equal to 2, then we have something like x square plus 2. And note that here it was trivial to break it down as x times x, but I don't know what to do here. But what can we actually say here is we can sort of use this property. I claim that this is also reducible. And for claiming that this polynomial is reducible, I'll use this property that if there is a 0 of the polynomial in the field, then the polynomial is reducible. So here, if I put x equals to, it can be seen that if I put x equal to 1 here, then this will give me like 1 square plus 2. And 1 square is 1 itself. And so this will give me 1 plus 2. And since this is over Z3, so we'll be instead actually doing 1 plus 2 mod 3. So we'll get something like 3 mod 3, which is 0. We get the value of polynomial is equals to 0 over Z3. So over Z3, the value of this polynomial is 0 because 1 square plus 2 mod 3 will actually give me 0 only. 0 mod 3. So what we actually get is that x equal to 1 is a 0 of the polynomial over field Z3. So, and we know from this property that if there exists a 0 of the polynomial in the field, then the polynomial is reducible. So thus the polynomial x square plus 2 is reducible over Z3. So, yeah. So we are done with the first two options. So option B. So maybe I should like state state the definition of irreducible polynomials also, so that uh, maybe everything is a bit self-contained in this solution. So what is an irreducible polynomial f? So like I just want to write down a formal definition for this. So what I just said was a polynomial is irreducible if it can't be broken down into two factors which have degree smaller than the original polynomial. So maybe I should write it like this only. A polynomial Px over field F is called an irreducible polynomial if there does not exist any two polynomials Qx and Rx over F such that Px is actually equal to product of Qx times Rx and degree of Qx. So first thing is that for a polynomial to be reducible, it should not be written down as product of two polynomials. And these polynomials should have degree less, like basically px should not, we should not be able to write px as product of two lesser degree polynomials. So basically there should not exist two polynomials such that px is equal to qx times rx and degree of qx is actually less than degree of px. Degree of qx comma degree of rx is actually less than equal to. The polynomial is called an irreducible polynomial if there does not exist any two polynomials qx rx over f such that px is qx times rx and degrees of px and rx is less than degree of px. So what will be a reducible polynomial? It will be just opposite of this. So a polynomial px over field f is called a reducible polynomial if there exists two polynomials qx and rx over f such that degree of qx comma rx is less than degree of px and px is actually equal to qx times rx. So yeah. So this is definition of an irreducible polynomial. So yeah. And then we have this property for a polynomial being reducible, that if there exists a zero of the polynomial, then the polynomial is reducible. And from this property and the definitions, we got the answer for option A and C. Now for the option B, we have the polynomial as, what do we have the polynomial? The polynomial is x square plus 1 here, right? And so the polynomial is x square plus 1. So now if we try to use this property to find out reducibility, we can actually see that we'll not get any zero value for the polynomial. We'll not obtain any zero. Putting So I'll just state the polynomial as fx to be a bit more so that it is a bit easier to write. So fx is x squared plus 1 and it's defined over this field z3. So over this field z3, the only values which x can take is 0, 1, and 2. So what does this mean? F of what will the value of f of 0? F of 0 will be 1. F of 1 will be 1 square plus 1, which will be 2. And f of 2 will be the third value will be f of 2, which will be 2 square plus 1, which will be 4 plus 1, which will be 5. So 5 mod 3 is 2. So f of 0 is 1, f of 1 is 2, and f of 2 is also 2, right? So as we see that the polynomial does not have any zeros because all three values have a non-zero value. So hence fx does not have any zeros. So one thing to note is that So another thing to note is that maybe I should write down this property also. So this property is quite similar to what we do in algebra also. That basically, if there does not exist a zero of the, so if there exists a zero of the polynomial, let's say alpha is a zero of the polynomial, then x minus alpha should be a factor of that polynomial. And it's an if and only if condition. So what I mean to say is a polynomial maybe what should I write it as? Over a field f of a is equal to 0 if and only if x minus a is a factor of f of x. So this is a straightforward property. Like this property and this property are sort of corollaries of each other, because if x minus a is a factor of f of x, like if a is a 0, then x minus a is a factor. And if x minus a is a factor, then the polynomial gets reducible over f. So that's why from this property sort of follows. Maybe I should write this property first. That's why. So we sort of have this property that f of a is 0 if and only if x minus a is a factor of f of x. And why did I define this sort of property? So we first of all, we know that f of x does not have any zeros. And this property stated that if there exists a zero, then polynomial is reducible. Now, if it does not have a zero, we are not sure that it can be reducible. It can also be irreducible. So we want to do something else to find out whether this polynomial is reducible or irreducible. So we do this by contradiction. So first of all, we can't directly use the property to say whether f of x is reducible or not. We can't directly use the property, but what we actually can do is we'll claim that we'll claim that f of x is actually irreducible. And how will we do this? So this is a claim. I have not provided any proof for this. So the proof for this will be along the following lines. So how do I prove this? To prove this, we do this by contradiction. So we do this by contradiction. And maybe I should write this as properties. Maybe I should label these properties also. So property 1. So this is definition. This is not a property. I should label this as property 2. This is property 3. So yeah. So we sort of do this by contradiction that f of x is irreducible. And how do we do this? So suppose f of x is actually reducible. So we know that f of x is actually a degree 2 polynomial because x, it is written as x square plus c. So power of highest term is 2. So suppose f of x is reducible. So what does this mean? This means that that is f of x is actually equal to q of x times r of x. So there exist two polynomials qx and rx such that f of x is equal to, there exist qx and rx such that fx is equal to qx times rx. But we know that as degree of and what do we know? We also know that degree of qx should be, degree of qx and degree of rx should be less than 2. Like should be less than like definition for being irreducible is that degree of Rx and Px should also be Qx and Rx should also be less than Px for being reducible. So what does this mean? So if Qx and Rx should have a degree less than f of x. So this is less than the degree of f of x. So what does this mean? This implies that uh, degree of Qx and Rx is actually less than 2 because degree of f of x is 2 because f of x is nothing but x squared plus 1. But note that we also know that since f of x is qx times rx, we know that degree of f of x should be actually equal to degree of qx plus degree of rx. Since this is a property which which we have from um, polynomial multiplication over fields. This property was defined here, like in property 1, that if px, qx, and rx are polynomials over a field and px is qx times rx, then degree of px is degree of qx plus degree of rx. So by property 1, we have that degree of qx plus degree of rx is actually equal to 2. Degree of qx plus degree of rx is actually equal to 2. So we have something like individual degrees are less than 2, but the sum of the degrees is actually equal to 2. And note that uh, degrees can just be like integers, like non-negative integers. A degree of a polynomial can only be like 0, 1, 2, 3, 4, and so on. So, but let's say this statement is statement 1. And let's say this statement is statement 2. And now what I'm trying to claim here is that, so see, degree of qx and rx is less than 2. So both of these can only take the value 0 and 1. So the only possible combination is what I'm trying to claim is that since degree of qx plus degree of rx is also equal to 2, the only possible combination is 1, comma 1. Like degrees are less than 2, so qx can take the value, this degree of qx can take the value 0 or 1. This also takes the value 0 or 1. But the sum of these two values should also equal to 2. So the only possible combination is when both of these values take a 1. So since degree of a polynomial is a non-negative integer, by 1 and 2, we get that degree of qx is actually equal to 1 and degree of rx is also 1. So degree of qx is actually equal to 1, which is also the degree of rx. So like this argument is a bit long, but like this argument may feel a bit long, but it's a quite straightforward argument. First we said that we do contradiction and we say fx is qx times rx. So now we know that degree of qx and rx is less than 2 because we said that fx is reducible. And also we know that degree of qx plus degree of rx is actually equal to 2. So the only possible combination which satisfies this is that degree of qx is 1 and degree of rx is 1. So what does this mean? This means that so if degree of qx is 1, then like qx is a linear polynomial, right? So what does this mean? This means that uh, this implies that qx is of the form ax plus b, or I can just write it as x plus a. So since degree of qx is 1, as we should write like this, as degree of qx is 1, So since it's a degree 1 polynomial, so it's a linear polynomial. So it's of the form of something like x plus a, where this a is something which we don't know. A would be from this field Z3 only, but A is uh, like the QX will be some of the form something like x plus A only. But from property 1, we know that. So what does this mean? So this means that actually this means that x plus A is a factor of fx. So so we are sort of saying that fx was this, and if fx can be written as something like, and if like fx can be written as something like fx is qx times rx, and this qx is of the form x plus a, then we are essentially saying that x plus a is a factor of fx. But from property 2, from this property which we had defined, a polynomial f of a is 0 if and only if x minus a is a factor of fx. So if x plus a is a factor of fx, then f of minus a should be equal to 0. So I hope you guys get this. By property 2, we get that f of minus a is equal to 0. So property 2 states that over a field f of a is 0 if and only if x minus a is a factor of fx. What we have till now shown in our proof by contradiction is that x plus a is a factor of fx. And if x plus a is a factor, since this is an if and only if, we'll get that f of minus a is 0. So we get f of minus a is 0, and this is a contradiction. And why is this a contradiction? It's easy to see because we had already shown that fx does not have any zeros. But here we get that minus a is a 0, which is not possible as we had already shown that putting all three values, we do not get any 0. As we had already checked that f of x does not have any zeros over Z3. So what does this mean? Hence, so we assume that fx is irreducible. Okay, so we claim that fx is irreducible, and how did we do this? We assume that fx is reducible and then obtained a contradiction. So actually fx is not reducible, and this means that fx is irreducible. So hence f of x is irreducible over Z3. So this is the whole argument for this option B. So even though this seems like a fair amount of work, but note that this can be sort of thought orally also. Like if we just assume that it is reducible, then fx will be qx times rx. Then the sum of degrees should be 2, and each of these degrees should be less than 2. The only possible combination is when both have degrees 1. But if they have degree 1, then uh, then they should also have. So basically, whenever a polynomial has a degree 1 factor, then we can say that polynomial should also have a 0. But we already checked that this polynomial does not have a 0, and so we obtained a contradiction. So I hope the flow of the argument in this is clear to everyone. So maybe if it's not clear, I would advise you guys to look at it again in the recording or when I upload this PDF. So yeah. Other than that, like if you guys have any doubt in this argument, or maybe you can ask me via chat also for now. Okay, so since no one is typing, I'll just assume no one has any doubts till now. So we see that uh, for c equals to 1, the polynomial x square plus 1 is actually irreducible. So the question was asking values of c for which the polynomial is irreducible. We showed that for 0 it is reducible, for 2 it is reducible, and for 1 it is irreducible. So the option B is correct. So hence Option B is correct. I'll just underline this. Yeah. Okay, so the third question is done. Now we'll go to fourth question then. So fourth is a very straightforward question, just straight from the lectures. So I would expect you guys to have at least seen the lectures. If you are not, I'll advise you guys to see the lectures first. So yeah. So the question is asking select the correct options for the value of degree of polynomial, which can be used for n, t Shamir secret sharing. So uh, so this concept of n, t Shamir secret sharing has also been discussed already in the lectures, but maybe to just give a very high level overview for this. So in this n, t Shamir secret sharing, what do we do? If we want, we sort of create a polynomial which has we sort of create a so the main concept behind this uh Shamir secret sharing is that for a polynomial of degree k, if we want to find out all of its coefficients, we need k plus 1 values. Like let's say if I want to find out exactly a linear, like let's say there's a polynomial of degree 1, the polynomial is let's say ax plus b. Then to find out the values of a and b, I'll need at least two values of polynomial. Like I need to get f of 1, what's the value of f of 1, what's the value of f of 2, and so on. So I'll need any two values because if we are given just one value, then from a given single point, any number of lines can pass. So I need at least two values to fix what's the polynomial. So the secret behind this n, t Shamir secret sharing is the key part behind this is that uh, we first of all take a t minus 1 degree polynomial. And so for obtaining this t minus 1 degree polynomial, we'll need at least t values. So if we are given exactly t values, then we'll be able to obtain the value of the polynomial if the polynomial is of degree t minus 1. So what do? We initially take a polynomial of degree t minus 1 in the n, t Shamir secret sharing. Then we create sort of n instances. Suppose we have this we have a t minus 1 degree polynomial. Let's say the polynomial is f of x. I just take the values of f of x over n different values. Let's say I define f of 1, f of 2, f of 3 till f of n. And I distribute these different values to these different people. Like treat these values as f of 1, f of 2, f of 3 until f of n as some keys. And the polynomial is something which is a hidden thing. Like polynomial is a hidden treasure, like which can only be so the key here is the main problem is, let's say suppose I have a treasure and I want to I want that there are n people. I want to give a key of that treasure to all of those n people, like, but I don't want any single person to be able to open that treasure. At least when t of the persons come together, then they should be able to open the treasure out of total n people. So this t is something which I'll choose. So I hope this is sort of making sense. I'm just describing this orally. I'm not writing this down because this has already been discussed in great detail in the lectures. So just giving you an intuition of what happens. So suppose I have a treasure and there are n people among which I want to give the keys to the treasure. But I don't want a single person to be able to open the treasure trunk box, let's say. I want that at least T people should come together if they want to open the treasure. So if I want to do something like this, I can use this n, t Shamir secret sharing. The key idea behind this is that let's say the password for that treasure box is a polynomial of degree t minus 1. Let's say the password for the treasure box is a polynomial of degree t minus 1. Now to determine what's the polynomial actually, let's say I just generate for this polynomial of degree t minus 1. Uh, I obtain n different values. Let's say I obtain the polynomial's value at 1, f of 2, f of 3 till f of n. And I distribute one value to the first one. Let's say to the first person I give the value f of 1, to second person give the value f of 2, third person give the value f of 3, to another person I give the value f of n. So now each of the persons has it only one value to them, and they don't know what are the other values. So they can't determine what's the actual polynomial, which is the key to the treasure. Like the treasure opens once you know the whole polynomial. But if I only know what's the value of f of 1, I don't know what's actually f of x, right? So I need to ask at least t people. Like there should at least t people should come together, and then I'll have a set of t values. And from the set of t values, I'll be able to obtain the polynomial of degree t minus 1. And so I'll be able to open the treasure. So I hope this sort of makes sense. So anti-Shamir secret sharing makes sense I want when I want that one person should not be able to open a treasure box, but only the treasure box should open only when at least t people come together. Because when those t people come together, I can determine the polynomial, which was of degree t minus 1. And because of that, I'll be able to open the treasure box. So I guess from the description itself, the oral description itself, you can see that the degree of polynomials which can be used for this n comma t Shamir secret sharing is the polynomial of degree t minus 1. So answer is polynomial should have degree equals t minus 1. Like, like this is something which has already been discussed in the lectures, and there's not much to it. The only idea behind is that the degree t minus 1 polynomial can only be solved when at least t people come together. So yeah. So yeah. So hence option A is correct. So this question is straightforward. Like you just need to know what n comma t Shamir secret sharing is, and you will be able to answer this. But I just want to describe this procedure in an overview, like what is n comma t Shamir secret sharing actually is. So yeah, if you guys have any doubt in this, then maybe you can ask me via chat, or maybe I can move on to the last question. Okay, then. So maybe I guess since no one is typing, I'll just move on to the last question. So last question is nothing. Another question like which does not have any thinking part. This is more of a revision based part. Like if you have seen the lectures, like this is just an information based part. Like obviously this information also has proofs in the lectures, but rather than the proofs, I believe the final results matter. Like these results are something which matter rather than their proofs. So yeah, like their proofs are also important, but results are also important. So yeah. So like this fourth question also, like you just have to know that there's degree t minus 1. We define this degree t minus 1, and the reason behind it is that we need at least so that t people can open the box. So here uh, so choose the correct options from the following. So we'll go option by option. The order of a field f divides n, where n is equal to the size of the field. So this is more of not an information based question exactly, but yeah, this is a property which you should remember. And this is a very important property for the fields. And yeah, so the proofs are obviously discussed in the lectures, but like along with the proofs, you should also remember these properties because these are very key properties related to fields. So yeah. So option A is like correct. You can see this in the lectures. Correct as discussed in the lectures. Similarly, option B says like also if you have any doubt about what's the definition of order of a field f, what's the definition of characteristic of a field f. The characteristics definition I had already defined, but if you don't know what's the order of a field, maybe you should watch the lectures and see what's the definition for order of a field. I don't want to discuss those definitions again. So characteristic of a field divides and where n is size of the set of field. So this is actually also correct. So this is also correct as discussed in the lectures. So yeah. So actually these two options are straightforward information based question. The third option says that if a polynomial is irreducible over ZPX, where P is some prime, then it has no roots in ZPX. So this statement I'm claiming like this is something which I have already discussed. Like, it's saying that if a polynomial is irreducible over ZPX, then it has no roots. And this is a property which I have sort of already discussed here in this property 3 here. Like if here I have said that if there exists a zero, so zero and roots of a field are essentially the same thing of a polynomial. They're the same thing. So if there exists a zero of the polynomial, then the polynomial is irreducible. So what will be the contrapositive for the statement? Like we know that contrapositive and the statement itself are equivalent. So I know that this property holds true that if there is a zero, then polynomial is reducible. So what will be the contrapositive? So contrapositive will be if the polynomial is irreducible, then there does not exist a zero, right? The contrapositive of A implies B is not B implies not A. So A implies B's contrapositive will be not B. So if polynomial is irreducible, this implies not A. So then there does not exist a zero of the polynomial. So actually this property can be reworded as if the polynomial is irreducible, then there does not exist a zero of the polynomial. And this is essentially what the option C is saying. If the polynomial is irreducible, then it has no roots, or let's say no roots or no zeros. So this option C is actually correct because it's just option C correct, as it's the contrapositive of property 3. So the property 3 was this: if there is a zero, then the polynomial is reducible, and its contrapositive is exactly this option C. And option D says that if a polynomial has no roots where P is some prime, then it is irreducible. So this is actually converse of option C. So option C says if a polynomial is irreducible, then it has no roots. Option D says if a polynomial has no roots, then it is irreducible. But note that while discussing the question 3, while discussing these properties, I had already said that the converse is not true. Like I had only written this statement that if there exists a zero, then polynomial is irreducible. But like if there does not exist a zero, it does not mean that the polynomial is like if there exists a zero, polynomial is reducible, but it does not mean that if there does not exist a zero, then the polynomial is irreducible. Like if there does not exist a zero, then the polynomial can be reducible as well as irreducible. Like we don't know. So that's why we had to, in this option B, we had to do this via proof to actually show whether it is reducible or irreducible. So yeah, so option D states that if a polynomial has no roots, then it is irreducible. And what I'm trying to say is that this property is actually incorrect. Like, uh, because like intuitively, how can you see why why this property is incorrect? Because if a polynomial has no roots, it just means that there is no linear factor of the polynomial, right? But how do we define the irreducibility over polynomial? A polynomial is irreducible if there does not exist any lower degree polynomial factorization. So let's say I take a polynomial of degree 5, and if the polynomial has no roots in the field, then it means that the polynomial does not have any linear factor, right? But there can be two non-linear factors for that polynomial, right? For example, let's say x to the power 5, we take the polynomial x to the power 5. It like x to the power 5 also has linear factors, but it also has non-linear factors, right? Something like x squared times x cubed. Or let's just say the polynomial which is something like x squared plus 1 times x cubed plus 1, or let's say x squared plus 1 times x to the power 4 plus 1. Let's say I take a polynomial of degree 6, which is something of the form, I'm just giving you a high level intuition why this statement is incorrect. Let's just take a polynomial which is multiplication of x squared plus 1 with the polynomial x to the power 4 plus 1. Now that polynomial sort of has no roots. Of course, I'm defining this polynomial over all real numbers are, but here we are talking about just the field ZPX. But trust me, like you can get examples similar to this in the field ZP also. So over the field R, if we have the polynomials as x squared plus 1 and x to the power 4 plus 1, then those polynomials do not have any roots, right? X squared plus 1 does not have any roots, any rational root, any real root, basically, any rational root, basically. Or let's say any real root also. It has a complex root, x squared plus 1. Similarly, x to the power 4 plus 1 also does not have any real root. So their product will also not have any real root. But as we see, the final polynomial of degree 6 is actually reducible, because that degree 6 polynomial is actually reducible to two lower degree polynomials of degree 2 and degree 4. That's sort of the intuitive idea behind why this statement is incorrect. And you can find similar examples among the field ZP also. For now, I defined it over the field R, but you can find similar examples over the field ZP also. So this statement is sort of incorrect. Okay, then. So this was the last question which I wanted to discuss. So, like, if you want to choose the correct option, so here only options A, B, C are correct. Hence, options A, B, and C are correct. So, okay, then. So this was the last question for the day which I wanted to discuss. So I guess this culminates our 12th problem solving session, and so like our all problem solving sessions. So yeah, so uh, I guess I hope you guys enjoyed these problem solving sessions. So since we have like 5-6 minutes left, so Jitesh, if you have any doubts in something which we discussed today, uh, maybe I can try to answer your doubts. And if you don't have any doubts, then maybe we can close the session. So, okay, so Jitesh has no doubts. So cool then. So maybe since no one has any doubts, so I guess we can close the session. And like just a reminder, we'll also have a summary session. Like this was our last problem solving session. Now we won't have any more, but uh, we'll have some sort of a summary session tomorrow from 10 p.m. onwards, a 2-hour session. So yeah, so hope to see you guys there. And yeah, I guess I'll close the session. And yeah, thanks for joining everyone. So bye bye.